The AK-47 is widely regarded as an indestructible machine, a weapon capable of being buried in mud, left for decades, and still firing without fail. For decades, a persistent explanation for this reliability has circulated among firearms enthusiasts: the idea of loose tolerances. The theory suggests that the rifle functions in harsh conditions, specifically because it was manufactured with sloppy internal clearances, giving dirt and debris room to move without jamming the action. This 1978 East German repair manual provides the empirical data to test that theory. It serves as a strict diagnostic roadmap. Treating this document as a forensic guide, we will map the mechanical boundaries and observe how the system fails. What emerges is proof that a functioning AK-47 requires exact physical relationships. Pushing the internal components past rigid engineering limits results in predictable systemic malfunction. The mechanical cycle begins with thermodynamics. When the primer ignites the M43 cartridge, the propellant burns, generating a rapidly expanding volume of high-pressure gas that pushes the bullet down the barrel. Near the muzzle, a small aperture called the gas port captures a fraction of these expanding gases and channels them upward into a cylindrical housing known as the gas tube. Striking the face of the gas piston, this sudden thermodynamic pressure translates directly into mechanical energy, violently driving the attached bolt carrier rearward. This text from Section 3 of the NVA manual documents the exact threshold where this gas system fails. Armorers are instructed to measure the radial play between the gas piston and the gas chamber walls. If the gap between them is greater than 0.2 millimeters, the piston must be replaced. A gap exceeding 0.2 of a millimeter creates excessive volumetric space. The high-pressure gas simply blows past the piston head, bleeding off the kinetic energy required to push the heavy bolt carrier assembly all the way to the rear. The cycle halts entirely. The powerful, continuous cycling of this gas-operated rifle system relies absolutely on tight, strictly maintained volume-to-pressure dependencies. The system breaks down the moment its internal clearances become too loose. As long as the gas seal holds, the carrier assembly continues its violent linear travel toward the rear of the receiver. Machined into the underside of the bolt carrier is a precise, curved channel called the cam guide. As the carrier moves straight back, this guide acts as a lever against the bolt itself, forcing it to rotate on its central axis. This specific rotation clears two thick steel locking lugs from deep recesses cut into the front trunnion, physically unlocking the breech. Now free from the trunnion, the bolt slides backward alongside the carrier. An extractor claw grips the rim of the spent casing, pulling it from the chamber until it strikes the ejector and is expelled from the rifle. Having bottomed out against the rear of the receiver, the tensioned recoil spring drives the entire assembly forward again. The bolt strips a fresh cartridge from the curved 30-round magazine and feeds it directly into the chamber. In the final fraction of forward movement, the cam guide forces the bolt to rotate in the opposite direction. The locking lugs slide back into their trunnion recesses, sealing the breech. The rifle's ability to safely contain thousands of pounds of chamber pressure depends entirely on the synchronized geometry of these cam paths and locking lugs. To understand how the weapon resets for the next shot, we look at the fire control group, the mechanical timing center responsible for releasing the hammer. When the external safety lever is pushed to the lowest position, the rifle is in semi-automatic mode. Here, the trigger and an internal catching mechanism, called the disconnector, are free to move. During the ejection cycle, the rearward movement of the bolt carrier physically forces the hammer down flat into a tensioned, cocked position. While the shooter still has the trigger squeezed, the spring-loaded disconnector catches the hammer and holds it in place. The shooter must physically release the trigger to reset the sear and fire another round. The East German manual details a highly dangerous malfunction related to this exact mechanism, where the weapon fires continuous bursts while set to single fire. The documented cause is microscopic wear, specifically the rounding off of the sharp cocking surface on the hammer or the nose of the disconnector. If the sharp, defined geometric edges of these parts degrade even slightly, the sear engagement fails. The disconnector lacks the friction required to physically arrest the spring-tensioned hammer. Without the disconnector holding it back, the hammer simply follows the returning bolt carrier forward. It strikes the firing pin the moment the bolt locks, creating an uncontrolled, automatic runaway gun. The ability to fire a single semi-automatic shot relies heavily on rigid, sub-millimeter geometric engagements between small, hardened steel components. Moving the safety lever up to the middle position selects fully automatic mode. In this state, a physical bar rotates down, completely blocking the disconnector from moving and removing it from the firing cycle entirely. The weapon now relies on a separate component, the Autopsy, to hold the hammer back while the action cycles. The Autopsy is a mechanical trip. It will hold the hammer indefinitely until it is physically struck by the forward-moving bolt carrier. The placement of this trip is exact. The geometry guarantees the bolt carrier will only strike the Autopsy at the exact microsecond the locking lugs have fully rotated and secured themselves inside the front trunnion. If the hammer dropped a fraction of a second earlier, the firing pin would strike the primer before the bolt was locked. The expanding gas pressure would blow the unsecured breech backward, destroying the receiver and likely severely injuring the shooter. Fully automatic fire is an incredibly precise mechanical sequence, completely governed by the bolt carrier's final millimeter of forward travel. Pulling back from the micromechanics, it is clear that the AK-47 is a thermodynamic machine operating under immense heat and pressure. It is subject to friction, wear, and physical deformation, just like any other engine. This NVA manual table lists the highly specific tooling required to keep the weapon within functional thresholds. Armorers tested against exacting tolerances. Thawing thin protrusion is measured to 1.52 millimeters. Headspace gauges verify bolt lockup, rejecting the weapon if it strays between 32.85 and 33.15 millimeters. This documented reality of strict go-no-go limits sits in direct opposition to the pop culture image of a maintenance-free rifle operating with loose internal gaps. The weapon functions because of the precise choreography of gas expansion, volumetric pressure limits, camming leverage, and sharp sear engagements. The AK-47's legendary reliability is a product of meticulous engineering boundaries designed by Kalashnikov and the strict empirical standards enforced by the armorers tasked with maintaining them.